This video is supported by the National Science Foundation.
So now we have a working model. Let's start our training loop. To begin our training loop, let's define our loss function and our optimizer. So the loss function we'll be using is the torch.nn, that cross entropy loss, which is used often for classification and multi-label, or it's used for classification prediction. And our optimizer will be the atom optimizer. And when initializing the optimizer needs to know what parameters, what weights of what model it will be updating during the training loop. So we'll pass in the parameters of our model, which is a property or a function, on an NN module, a torch module. And we will set our learning rate to be, let's have a variable up here holding that. Learning rate to 1, e -3. So 0.001. And before I forget, I'm going to come up here and change my image size for our model to the appropriate 32 by 32. And I reran that cell to make sure that that was defined and initialized properly. Let's move this to the top. So now let's use that batch we had from the previous cell and just pass some information into our model. Let's pass that batch into the model and calculate a loss to test this loss function. First, I'll run the loss cell to make sure that is initialized. And I will get the predictions of our model passing in the batch. And I'll move the batch to my device. So this is where I'm seeing I can use that device property that we started at the beginning, that we built at the beginning. I'll move the batch onto the GPU and give it to the model. The other thing I need to do is make sure that the model is also on. The device is also on the GPU. So I'll run that cell again. Back to the bottom. And calculate our loss by, I'll also do this here, targets. Maybe I can do batch equals batch.to device. And then I will pass the batch in, and I will do targets equals targets.to device. And then when I calculate the loss, I just use my loss function and pass in the predictions and the targets. And then I will grab some code here, just some print statements. So here I'll print out the shape, the data type, and the device that each tensor that I'm working with is. Run that. And I see that my predictions are as expected, a batch size of 64, 10 numbers in the predictions, 10 logit numbers. It's the logits of the logit output of the model. Of type float32, and all of my tensors are on the GPU, my CUDA GPU. My loss at the end here is, I can see that the loss is 2.3, the actual number doesn't matter, but what I can see is that the output is a tensor with a single number in it on the device, on my GPU, and it carries with it some extra gradient information, the reverse gradient function that is used when the loss is, during the backward pass. So when I'm doing backpropagation to calculate the gradients in the reverse computation graph, that information is used on each of the tensors, and during the backpropagation algorithm, it'll step back. But sometimes if I want to just get the raw value, the number that is my loss, I can grab that quickly by doing loss.item. And sometimes you might need to do loss.detach to detach it from the computation graph and then move that tensor to the CPU explicitly, and then call .item. That can help, or I can also call .numpy to automatically turn it into a NumPy array. I can run that again, though I don't see it exactly. I am turning this into NumPy. If I don't have the CPU call here, if I try to run that, it can't convert the tensor directly to NumPy because it's not on the CPU. So you do have to have this detach CPU NumPy. All right, so we've tested our loss function. We know that we can pass the batches through our model successfully. So now it's time to get into the nuts and bolts of the training loop. All right, to begin, let's create a new cell. So this will just print out a prompt that we're starting to train. I'm going to keep track of the best loss, right? The lowest loss that I have during my training loop. This min delta is a value that we'll use as a metric or a measure to decide whether or not we have convergence, if the model has converged, if the model has stopped improving. So if the improvement is smaller than this min delta, we'll consider it a non-improvement. You can think of it that way. And I'll also keep track of the validation losses and the training losses during my for each epoch during training. And this is the stats dictionary I'll use to help update my progress bar. And I'll just set the max epochs to 100 for now. Very unlikely that we'll actually train to 100 epochs, but if the model trains all the way out to that, we want to have it stop at some point, and we'll use that to iterate as we go. So the first thing I'm going to do is I'm actually going to implement the necessary steps for a single training step. So what we want to do, we've kind of already seen this a little bit, is we want to get the model predictions. And we get pred equal model, right? And we'll pass in the batch. We'll assume that the batch needs to be moved to the device. And then we calculate the loss, which we've seen already, right? So we use our loss function, and we'll pass in the predictions and the targets. And we'll assume that those also need to be moved to the device, because as they come out of the data loader, they're not yet on the GPU. And we'll zero out our optimizer, because this will happen. We want to make sure that our optimizer, the gradients, we can not do this and accumulate gradients. There are some algorithms that allow you to do that, or that has some benefit in some algorithms. But in this case, we're just going to make sure that we zero out the optimizer weights, the optimizer values, and then we are backward, or actually we'll call this the calculate. And here on the loss that we get back, we just backward. So calculate the gradients, and then we perform our weight updates. And on the optimizer, we call that step. So this needs to happen every single training step. So to make it a little easier to write our training loop, I'll just take these 4 steps and wrap them in a function. And I'll take in a batch and targets. And I'll just allow this function to use the sort of, in this case, the global model and loss function. You could also implement this where you pass in a different model and a different loss function. But in order to keep things kind of simple, I'll just pass in a batch and targets. And then at the end, after those, after all the steps in the training, or after all of the calculations in this training step, I'll return the loss value. And that'll make it a little bit easier to see what we're doing in our training loop. So with the training loop, we will iterate up until epochs. And I'm going to also wrap our data loader in a progress bar. So this is where we'll get our nice progress. I'll just wrap our train loader and give it the total len of our train loader and a description. So we can print something. And let's say epoch. So now train loss equal to 0. So I'm going to keep track of the training loss so I can average it. I'll make sure the model is in training mode, because this also, since it iterates, I'll be in after validation or before validation, I'll set it into eval mode, and I'll make sure that the model is prepared to train. The weights can be updated. And here I can get the batch index and the tuple that is returned from the trained loader by wrapping the progress bar, enumerate call. And maybe I can make this a little smaller while we're working here to make it a little easier to read. So now, since I have my training step, I can just get the loss and train step and pass in the batch and targets. I will keep a running sum of my losses, getting the raw value of that number. And then I'll update the progress bar. So basically every five batches, I'll set the postfix. So there'll be a set of key value pairs at the end of my progress bar based off of the step loss. And I will also append my stats, which I'll be updating with other statistics later. And this will calculate the average training loss And now we'll implement our validation loop. So each epoch will have a training loop where the model will see all of the training data in our training split. And then we will iterate similarly through our validation data to calculate our validation loss. So on the data that the model has not seen during training. And I'll also do the same thing where I can say val progress, and I do the same exact thing where I'm just passing in the data to the model. And then I will also update the running val loss total. And the other thing that I'll do during validation, just to make sure that I'm not worried about gradient information, I can wrap this in a no grad context. At the end, I'll calculate my average validation loss. Now that we've implemented both our training and validation steps for this epoch, we will use that validation loss to check for convergence. We'll see if our model has stopped improving. And we can do that with val loss minus our min delta is less than our best loss. If that is the case, then we know that our model has improved, and we want to keep track of this new best loss. And we will update our stats here with that best loss. And we'll keep track of something called patience. And we're going to reset the patience actually here. And this patience is going to say that we're going to, if the model doesn't improve for 5 epochs, that's our patience is 5. If the model doesn't improve for 5, we will stop training. Also, if the epoch index is greater than 0, so not the first epoch, we will save our model. So this is how we can actually save and keep track of our best performing model. And we're just going to save the state dictionary. And we'll go through how to load that as well. And I'll call this models/best. If it has not improved, we will update our stats. Patience will equal stats.get patience. If it's not yet set, we will just return 0, and we will add 1 to that. So stats, since stats is a dictionary, I will try to get the patience. If it doesn't exist yet, if I haven't set it, it will return 0, this line, and then that 0 will be added to 1, and the patience will then be set to 1 the first time it runs. Otherwise, it'll get that value, return it, and add 1 to it, increment the patience. And then I can say if stats.get patience 0 is greater than 5, we will print converged and break from our training loop. And at the end of training, we will print done. An important thing that I forgot to do, I believe, is to ensure that during validation or before validation runs, I make sure the model is in eval mode. I don't want the, I want to just double check and make sure that these passes to the model doesn't include gradient information, and that I'm not necessarily allowed to update any weights. I want the validation to be, the model to be fixed during validation. So at this point, I'm going to try to run training and and see if everything is working. And because I don't have a directory created for models, I failed. So what I'll do is I'll create a model root equals path models, and then I can say model root dot make director parents equals true, exist. Okay, so if the second time it runs, if it's already there, it won't raise an error, it'll just work. And then when I go down to my save, instead of passing it this way, I will use str model root /best.pth. So what's nice about the path class is that in order to concatenate and join paths, I can use this syntax where I just use this backslash and the variable name to concatenate into a single path. I did notice a weird bug where the epochs were not updating for training. So let me double check something there. I am enumerating over the loader and not the progress itself. And that Should fix that. And now for the fun part, where we can do some analysis on our model. We can see that for me here, it converged after 28 epochs. And I can actually see as I was watching the training happen, a couple times, actually, the patience was increased to 1 or 2 or 3, and then it actually was reset because for a couple of epochs, there was no improvement, and then there was again improvement, and so on. So we should take a look and see what did that curve actually look like. So I have my train losses and my validation losses saved as lists. So I'll grab some plotting code really quickly. What I'm doing here is I'm creating, using Seaborn, I'm creating sort of a plot style context, using Seaborn just for the styling in this case. I'm creating a figure that's a fairly small figure, 3 by 3, plotting the train losses, giving them a train label, validation losses, giving them the label of validation, adding a title, making sure the legend is visible, and then showing the plot. Now I can see here the training curve continues to decrease, so it's getting better and better and better, but we can see that the validation improvement is changing in a different way. It's changing slower, so I sort of started to level out. And if I increase the patience to say 10 or 20, it might continue to train for a very long time, but would it continue to get much better? Maybe, maybe not. We could change our model a little bit to see if we can improve the loss. But before we start modifying our model, let's take a closer look at the accuracies of our predictions. And a nice way to quickly visualize how well we did in our predictions is a confusion matrix. So just to go through this code really quickly, I'm using some helpers from scikit-learn, the confusion matrix display class, and a function confusion matrix, which will help me build my confusion matrix. I'm also, I don't want to use the model in its current state, right? Because the current weights that I have on my model in this code in memory are the weights that apply to the very, very last training step, or the last epoch, I should say. So what I want to do is I want to load weights that I saved during training, which were saved at models, and I probably can do this way. So I can use the torch.load method, giving it in the path to my state dictionary, loading those values, and then I can, on the model itself, there's a method called load state dict, that I can use to apply those weights to the model. And then I'm again making sure the model is in eval mode. Within a no gradient context, I'm creating empty numpy arrays to hold my predictions, my scores. So the predictions in this case will be the predicted class, and the scores are going to be the actual sort of probability value. How likely is it to be that particular class, and the targets, the labels. So I'll do what I normally do, right? I get the logits by passing the batch into the model. But in this case, since I'm not calculating loss, I need to use the softmax activation directly. So I'm taking the softmax of those logits across the columns, right? So each row in the logits is a set of 10 numbers, and I'm going to apply softmax to that, which means that that row will sum to 1, and the number that is largest will be the number with the highest probability that the model is predicting that class, the index, right? The column that number is in. And so when I call torch.max across, again, the columns, I get a tuple back of the value that is the maximum, and I also get the indices, the index into those columns. So I can get the index, which is the class, and the scores, which are the probabilities. I then just concatenate that to my numpy arrays, and use those results, the targets and the predictions, to build my confusion matrix. I pass that confusion matrix information to my confusion matrix display from scikit-learn. I can call display plot, which will do all the nice visualization for me. And then I'm calculating the overall accuracy, right? So I'm calculating overall how many of the predictions are equal to the targets. And then I'm just dividing by the total number of targets, the total number of labels that I have. And then I'm printing out the index to class mapping just as reference to match the indices that I'll see in my confusion matrix to the actual classes we have in our data. If I run that and if all goes well, And note that I'm also using the test split. So this is data that was not seen during training at all, right? This was not the training split, not the validation split, but the test split that was held out during training. And I have this nice confusion matrix where I can quickly see the count of how many true labels were actually predicted as that, right? So in the diagonal, I'm seeing how many true, like for 0, 0, I'm seeing for the true label 0, how many were predicted as 0, and I see 502. So along the diagonal are sort of the true, the correct predictions, and the off diagonals are where the model got things wrong, right? I can see counts for how often when the true label is 5, the predicted label is 3. So I can kind of get a sense that that's a pretty high number, that the model is often predicting 3 when the underlying true class is 5. And that might be a signal for me to double check those classes and to see what's going on there. Well, let me see, where did it print the things? So, okay, so 3 and 5. So right now, it's struggling, the model, our current model is struggling with a distinction between cat and dog. So I'm not sure why I'm such weird, there we go. So the model is struggling between predicting, it is predicting cat when the underlying label is dog. So that would mean maybe those, if I take a closer look at those images, I can try to see if there's an issue there, or maybe the reason is that most of the animal pictures are all on green backgrounds. So the model is not actually using the animal information. Maybe the model is using the green background to predict whether or not it's in that class, but it's getting it wrong. It hasn't learned properly that class. And you can use this as a quick way, as a quick guide to start to look at, if you're in a classification setting, what parts of your data the model is struggling with, what you might need more representations in your data. You might need more representations for certain classes to improve your model's performance there. And can give some guidance as to that. The next thing we'll want to take a look at is the actual score distribution of our outputs. So I'll grab some extra plotting code here. So here, let me make this a little bit easier to see too. So I am again iterating through my scores and targets. So I'm getting the probability score, and I'll change this to score just for clarity. So I'm the zip function from Python helps to zip these. You can think of the two arrays being brought together. Like a zipper, and it returns a tuple of each of the entries, right? So I can use that, and I'm wrapping them in a dictionary with two keys, and then giving that list to the pandas data frame. So now I'll have a scores data frame similar to what I did with the splits previously, and then I'm creating another Seaborn style context, and this time I'm actually using a helper from Seaborn to plot distributions, where I'm giving it the data frame, saying what I'd like to be plotted on the X, making sure that the labels are used, the label information is used to separate the counts. I'm stacking the distribution, so this will be a his plot, and I'm just setting the color palette, giving a title and showing the plot. And I'll run that. So now I can see quickly, I can take a look at this and understand, okay, how often am I predicting what? Like when the model is predicting a certain class, is it very confident it's that class? And again, these scores are the maximum value, the maximum probability in that prediction, right? So all of the other probabilities were lower when it's predicting that class. So we can see that most of our scores are around 0.4. Not very, very strong, right? The model is not super, super confident in its predictions right now. It's sort of distributed throughout. The distribution's not very, very strong. Some of them are predicted as very, very high, very, very confident. The model the model is very, very confident in those predictions. And we would then also, we can take that and find these particular predictions for those instances and analyze those instances as well. But this is a nice way to quickly see how confident my model is, and and then use this to derive what data samples the model is doing very, very well on, and which data samples, again, the model is struggling on. Overall, however, we see that our overall accuracy was not very good really the model is more or less guessing, even though it seems to be getting a fair amount of things right. Our overall accuracy was only about 50%. So really, we want to see, can we improve this? What can we do to our model to improve this? And to give that a shot, we are going to change from our multi-layer perceptron to a CNN. First thing we want to do is head it back up to our model class. And I'm just going to change our name here to CNN. I'm going to keep everything the same. I'm going to say this is the image shape that's going to be coming in. I'm going to change our HTIMs to the default to 128, 128. And I'm just going to add another 256, 256. But we need to change how we're building, right? We're not using linear. We're not going to use a linear model. We're going to instead use convolutional layers. So I can change this to conv 2D. And the first thing I'll notice is that if I look at the initializer for conv 2D, just hover here, instead of taking in a number of features, so the number of neurons, I'm actually giving it the number of in channels, so the channels of my data, which in this case are the number 3 for 3 channels of our image, but it's the sort of the number of kernels that will be used for this layer. And then the kernel size and kernel stride, so it's a different set of inputs. So in our case now, instead of calculating the in features, these are going to be in channels. And it's no longer the product. I'm not going to flatten things. It is actually the going to assume that it's the first number image shape. So it's just the first value in that tuple. That's the number of channels we want. And I'll change this back to in channels. And I'm going to do a nice refactor here. So I'll do n channels. And so that'll change all those variables. I'm no longer going to have a flattened layer. And then I need to just put inverse here. And I'm going to have a similar pattern where I'm using the out channels as HTIM. So that part is sort of the same. Kernel size, I'll set that to a tuple of 3 by 3. And after my convolutional layer, I'll just have another ReLU. So everything else is pretty much the same. But instead of having it be a single model here, I'm going to create a CNN block that is the sequence of CNN layers that I have. And I'll wrap those in my sequential. And then instead, I'm going to have the linear prediction layer be just my last linear layer will be this guy. And so now I need to figure out, okay, well, the output of this CNN block is going to go into my linear predictions. So calculate that. And I'm going to use my pattern of calculating the output of the model. Instead, I'll just calculate the output of the CNN block. So here I'm using the image shape again to create an example input, giving it the example input to the CNN model, getting the shape of that output. And I know that instead of flattening my input, I need to flatten that to be able to pass it into my my linear layer. So in order to calculate that, I'll say my end features is similarly I'll use torch.prop this time. And I'll say it's the out.shape first to the end, the first entry in that shape tuple to the end, right? So it's sort of the exact same thing that the flatten was doing. And I'll just take the product of those numbers, and that should be the number of features, this end features, that goes into my last linear layer. And again, having it sort of inside my initializer here, I could do this manually, but having it as a part of my code is very useful because I can quickly debug and check and make sure that any changes to hyperparameters that I make for my CNN, if I change the kernel stride or if I change other parts, which we will actually do in the next video, we'll add some extra layers to make this a little bit more interesting. We can make sure that it works right away when we're initializing our model. I think that's all we need to do. Oh, no, I need to. So now I have this CNN block feeding into my linear prediction, which will still take in that number of features that we calculate here, and then predicting over the same number of classes. I will then, instead of making this a sequential of the all of the layers, I will pass in the CNN block and the linear prediction layer. So now my model consists of both of those things. And I guess I don't need to have these be on itself. Make it a little cleaner. I'll do this. And so really I only have the one single property on my object as self.model. But the forward function stays exactly the same. Where I'm giving in the input, I'm assuming that that's going to be of the image shape batched, and I can return the logits. And then I will rename this to CNN. And I don't need to change the initialization, and I can run this again with printing out my new model. Oh, and I think I forgot to, remove this self. Must be a tensor, so let me try NP. There we go. So now I can see that the output shape that this is printing, this is the shape of the output of my convolutional layer, which is 256. So I'm outputting 256 sort of new images, you can think of it, but these are the outputs of those kernels, right, in each convolutional layer, and of size 3232. And those multiplied together give me the number of features into my prediction, my last layer, my prediction layer, and I'm still predicting 10 classes. So I will run this cell again. I'll run the next cell, reinitialize my loss and my optimizer. So I'm reinitializing my optimizer with the new parameters of this model. I will then run this sample to see make sure everything's working. Because I didn't run our batch has changed now. So I will rerun my data loaders to get a fresh batch. We're trying to re-override certain things, making sure that we're fresh in memory. This again. And I think I forgot to actually add the flattening. So I'll add the flatten layer back into my sequential model, and that should fix the issue. Run that, pass into our batch, and we are good. So now I've validated that everything was working. I can pass data back into my model, and I can rerun training. Now the training has finished. I can see that the model converged fairly quickly, or seems to have converged very quickly. After only 11 epochs. And so let's take a look at our training curves to see how we did. So interestingly, we see that the training curve continues to improve, but the Bayesian curve very quickly sort of diverges, starts to only get worse. This is sort of indicative of overfitting, where the model is getting better and better and better at what it sees during training, and worse and worse and worse at generalizing what it has seen in training to the validation split. So we've saved our best performing model here. Let's use that let's see what our confusion matrix looks like when it was at its best. And let's see if we've improved it all. So we have improved accuracy a little bit. We went from only 49% or 50% to around 65, which is still very close to guessing. And I would say that we still need to do some more optimizations to try to improve this. The model is still getting a lot of things wrong. This is by no means a state-of-the-art model for this task. However, we can again see that it's even this particular model, we've changed the model, but we're still struggling with that cat and dog prediction. I believe it's 3 and 5, yeah. And if we look at the score distribution of our model, we'll run the same code. You see a very different curve, where here the model seems to be more confident than the previous model, where a lot of the predictions are all the way up at 1. So we did improve a little bit, but we're still not doing well enough for our task, right? We wouldn't be able to use this model in production or out in the real world, or trust that its predictions are good. But we can again use this information to continue to iterate, and change characteristics of our model or hyperparameters of our model to do so. So in summary, we have used the CFAR dataset for an image classification task. We implemented and trained our own model, the MLP, and then we refactored that multi-layer perceptron to a convolutional neural network. We implemented our own training loop. We logged those validation losses, the training losses, to look at those metrics to see how our model was training. And we also implemented convergence checking with a simple sort of early stopping check to see how often the model is when the model is improving and keeping track of when it does not improve, allowing us to stop when it diverges or has converged. And then we visualized our classification accuracy with the confusion matrix to quickly see where or how many times the model is predicting correctly for certain classes and where the model is predicting incorrectly. And we can also get a sense for how often the model is predicting incorrectly for specific classes, which can give us insight into how we might want to refine our data set, improve our data set, or refine our model as well. We also looked at the model's prediction score distribution to see how confident our model is in those predictions for each of our classes. And we can use the combination of these two things as a really good starting point to do analysis of our data set and our model hyperparameters, the performance of our model's hyperparameters. And we mentioned that in reality, we would need to do this many, many times with different hyperparameters to get a better understanding of whether the issues are in our data set, maybe in our model's architecture. Is the CNN the right model architecture, since there's a ton in the model zoo to choose from? We can use this information to make better judgments as we iterate.